All right, Advanced Math Day, here we go. We got lesson 10.1.2, investigating data representations. This is more like a lab where we get some data and then we do a little bit of stuff with it. So if you're watching this video, you probably just missed this day, and so you need to catch up or something like that. So what we got here is a little golf tournament. We put a piece of tape with the dot on the ground, and then we made people stand like 6 feet away from it, and then everybody was like tossing pennies to see how close they could get to the dot. Now, the problem was if you didn't toss your penny so that it was kind of flat when it landed, sometimes it rolled and it went really far away. And so we got a lot of data from that. We got 40 pieces of information. So we went ahead, and this is where we just kind of wrote down all our information. Once you get a set of data, the first thing that you want to do is you want to arrange it from the smallest number to the largest number, because we're going to be looking at like minimums, medians, Q1, Q3, the 5-number summary basically. So you want to go from lowest to greatest. Now, if you have several numbers that are the same, you still need to write down all of those numbers. So if you start with 40 numbers up here, when you write them in order, you still need 40 numbers down there. So you might have like a 2, a 5, a 6, a 6, a 6, a 6, a 7, 8, 23, whatever. So if you have repeating numbers, you still have to write down those repeating numbers. So that was basically what we did on the first day. We got them all in order. Then we broke it up into smaller groups, and then the smaller groups were supposed to make graphs of their data based on different types of plots or graphs that you can make. So when we did that, we talked about the types of graphs we've seen before, maybe in this class or in other classes. First one that we looked at was a scatter plot. So I have this example of a scatter plot here, and we did this in the first semester. And we talked about when we would use a scatter plot. The first thing that we would do is we would use it when we have 2 variable data. So 2 variable data is when we have one thing that we're measuring and we're measuring 2 different things about it. So here we've got Old Faithful's eruptions, and we're looking at how long the eruptions last and then how long in between times it was. And what we see here is that there's a relationship between the length of the eruption and how long it took for the next eruption to happen. So we see that, and these are the 2 variables. We're looking at how long it's lasting and how long it took to get to that next eruption. So that's what I'm talking about with 2 variables. And we plotted these on an X and Y graph. We would do this with numerical data. Oops, numerical data, not numerical. Numerical. So we do it with numerical data, meaning numbers, instead of categorical data like we did at the beginning of this unit. Our goal for this one is to make a best line of fit or a regression line. So what we're trying to do with this is make a best line of fit or regression equation. And we do that so that we can predict or that we can model. So this is so that we can model the association between the 2 variables that we're looking at. In this case, the eruption duration and the time in between. So we want to model the association. So basically, we want to look and see how these 2 variables are affecting each other. In this case, we can see there's a positive association. It doesn't look like it's super strong association because they're so spread out, but there is a moderate association. Looks like we have some clusters going on there. So that's what we would look like, and that's what we would use it for. 2 variables when we have numerical data. Now, early in this unit, we had 2 variables, but it was categorical. Remember, we had the Pi phone or not having the Pi phone compared to the laptop or not having a laptop. Those are non-numerical situations. We were looking at categorical data instead, so not numbers. Next thing that we got here is a dot plot. Now, the dot plot only has 1 variable with it. In this case, we're looking at the number of goals scored. And you might be saying, Mr. Holcomb, but wait, when we scored one goal, we had 3 of them. There's another number, a second variable. That's not really a number. That's a frequency, how often it happened. So we're looking at one variable and how often it happens. So a frequency. So one variable and frequency. This is, of course, numerical data because we're looking at numbers down here. And we talked about in class that we probably don't want to do a dot plot for our 40 pennies that we threw because there were a whole bunch of different numbers. Usually when you're doing a dot plot, the range of your numbers is not that great. So you see here that there's not a lot of different data points. And you normally see in a dot plot that several of the data points have a high frequency. So here we've got 4 that had 3 goals. So when we do a dot plot, we want a small number of, I should have said small range, but anyways, you know what I'm talking about. So a small number of data variation. So we don't want a lot of different numbers to look at. And we want the numbers to have, we want the data points to have a frequency. So we want each point to be repeated. We're really looking for a shape of our data in this one. We'll talk about shape in the next section. So the frequency is repeated. So this doesn't really work with our data sets that we did. We didn't have a lot of stuff that was repeated. There were some, coin throws that were the same, but for the most part, we got a lot of different numbers. So this is not a good one for us. Histogram is also one variable. So over here, we've got the height of these trees in centimeters. And then this is not another variable, it's the frequency. So we're looking and seeing how often this occurs. Now with the histogram, oh, it's numerical, sorry. With the histogram, we've got these things called bins. Each of these are bins. And the bins have a range of values that fit in them. So the bins have a range of values. And you'll notice down here that in our bins, each bin has to have the same range. This has a range of 50 values in it, so from 100 to 150. This has 150 to 200, so all of them are a range of 50 wide. And then the height is the frequency. So this is saying, okay, from 100 up to 150, how many times did we have a tree that was 100 centimeters up to 150? And it looks like 5, maybe 4, I don't know, whatever. So maybe 4 had that frequency. That was the frequency of that one. So the bins have a range of values, and the bins have equal widths. Now these bins are always going to be next to each other. If I've got 150, which bin does it go into? It always goes in this one. So it always goes to the bin to the right. So this bin right here is talking about 100 and everything up to 50. The next bin is talking about 150 and everything up to 200. So this means that none of them had a height of 350 because this bin here goes from 300 up to 350. This is not our minimum number. 100 is not necessarily our smallest tree. Our smallest tree is somewhere between 100 and 150. So it doesn't give us a lot of specifics there. This generalizes our data. So when I say generalize, I mean that we can't really tell what our original data was. because we have these bins that are just ranges. One extra thing, if you're wondering how many bins to use, like why did they use 1, 2, 3, 4, 5? Why did they use 5 bins? Just in general, a good rule of thumb is when you're trying to look at the number of bins that you do, that a good way to tell how many you could do is to take the square root of the number of numbers that you're looking at. So in our case over here, we had 40 different penny tosses. So when you have 40 numbers, the square root of 40 is close to 6. So we decided in our class to do 6 bins because, you know, it works, whatever. You don't have to. This is just a good rule of thumb. Box plot, also called a box and whisker plot. This is for one variable data. Can't spell. It's for numerical data. It also generalizes the data similarly to how a histogram does, but does something a little bit different. And again, when I talk about generalizing, look up here. We know exactly what our data was. I know that 4 people had 3 goals here. If I could really see this, I could see, when they had a 2-minute eruption, I could find out exactly how long it was in between. These are not generalized data. This is exact data here on these, whereas these are generalizing it. So on this one, the big difference on this one is it uses the 5-number summary. The 5-number summary is the minimum, the Q1, the median, the Q3, and the maximum. In your book, in the methods and meanings section, I think it's in this section, methods and meanings goes back over the box and whisker. You should have done this in a previous course. If you've forgotten, minimum is the lowest number, maximum is the biggest number, median is the number directly in the middle of your data, Q1 is the middle of the lower half of your data, and Q3 is the median or the middle of your upper half of your data. Now this also splits it into percentages. This one tells us that 25% of our data falls in this whisker. 25% falls in this whisker, not whisker, this part of the box. 25 falls in this part of the box. 25% of our data falls in that part. So really what we look at is this box. This is the middle 50% of our data. Usually our best data, or the data where it's most indicative of what we're looking at, it falls in the middle. So we care about the middle usually more than what's on the ends. So our middle 50% is that box. All right, 2 more. Now we've got a bar graph, and you're saying, oh, isn't that just a histogram? No, not really. It's similar to a histogram, but different. It does have one variable. In this case, our variable is our favorite type of movie. And so we could have comedy, action, romance, drama, sci-fi. So that's our variable, is the favorite type of movie. And then this is the frequency, how often it's happening. So it's got a variable with frequency attached to it. On this one, these are not numbers, so this would be categorical data. Okay, so it does show us the frequency of each of our categories, or frequency of each subsection of our categories. You know what I meant. I can't spell again. We'll just call those choices or whatever. I don't know. All right. Last one, pie chart. Pie chart. So here we've got our pie chart. Again, we're seeing that it's one variable. It's the favorite type of movie. So one variable. And this is also, of course, categorical. The big difference on this one is we're looking at percentages instead of frequency. So this is almost like, this is like the version of the box and whisker because it's percentages, but it's categorical. Box and whisker was percentages with numerical. And this is kind of like the histogram where we're looking at frequency, but this is for categorical. So the stuff that we were looking at in ours ended up being probably a histogram and a box plot that works best. We decided to do both. So I'll show you what one of the students did to show you how these two can work together. So here they had 40 different throws. You can see up here, they've got their box plot on top. And woo, look at that outlier way out there, 340 inches. We can see that most of the throws were pretty close, 31 inches. But we had an outlier way over here at 340 inches. So that's pretty way out there. And here is their histogram. So here you can see that they chose 6 bins. These 2 extra bins out here, those are our outliers. So we didn't count those as the bins. So when we were doing our 6 bins, we were just doing these 6 here. And then if we had outliers, they would have their own bins. Notice that all the bins are the same width. These people made theirs a width of 20 units. So everything is 20 as they go here. And look, they had to skip. And then this bin shows up later on because it's an outlier. But the bins are still 20 apart until we get way over here for our last bin. And this matches up with the box and whisker plot above. So we can see here that 25% of our data, the upper 25%, is really spread out. Whereas the lower 25% of the data is not spread out. The middle of the data is not spread out. So it's only the top 25% of our data that is really spread out. So we would generally, if we're looking for associations between things happening, we'd probably say that we're more likely to be somewhere down here than in that top portion. So that's what it ends up looking with, and that's what we did for 10.1.2, the investigating data representations. All right, math hard. See you guys later. Bye-bye.